Now we're going to take a look at a case of a rod which has a non-uniform mass distribution, and the mass is going to increase linearly as you go from the left end to the right end. Now, when it comes to setting this up, it might be helpful to think about what might actually be causing a linear increase in the mass. I mean, because let's face it, if you have something like a piece of wire, you expect that piece of wire to have a uniform density. I mean, unless the wire gets thicker as you go to the right, how else would you end up with a greater linear mass density? So one way for you to possibly think about this is though what we're looking at is a piece of, say, plywood which is on edge, and so it does give us a little bit of thickness here like we have in the drawing, and you might be asking yourself, but how would I get that linear increase? And the way you would get that linear increase is simply by having the plywood cut out into the shape of a triangle. And so this is what we would see. So when you're looking at it on edge, all you see is this, just the thickness of the plywood, and we know that it's a triangle that's this long. But if I take that plywood and I stand it up on this thin edge, then what I might see is this, and now we have a triangle. Okay, so when you use a linear mass density, it's not necessarily because you're dealing with something that is only one-dimensional. It could be a 2- or 3-dimensional scenario where we only need to focus on one dimension. And so that's what the case is here, so that as I move to the right along this line, right, so as I move to the right here, we can see that each slice is going to have more and more mass. Compare that slice to this slice. And so as far as we know, looking at it from this perspective, all we see is that it's getting a little bit heavier, a little bit heavier, a little bit heavier, more and more mass until we get to the very end. So let's finish setting up the parameters of this particular problem. And what we're going to say is that the linear mass density, we used to write lambda is equal to mass per unit length. But this is no longer going to be the case when you're dealing with non-uniform distributions, because we assume that this mass here is divided up equally everywhere along the length of the object that we're focusing on. And that's not what's happening. So our linear mass density now has to be defined for us in a problem. You can't make assumptions about what the density looks like. So in this case, we're going to say that lambda is equal to alpha x. In other words, it's going to increase by some constant amount as we go along the x-axis. And that's what we see here with this triangle. We just have the slope of this line. Okay, so this is a key parameter to the problem. All right, now when we set this problem up, again, when you look in your textbook, you're probably going to be given xcm is equal to 1 over m times the integral of x dm. And this will not work for these situations of non-uniform distribution. And that has to do with when you use this version of the center of mass equation, we tend to use lambda is equal to m over L, and so we're going to run into some difficulties with that. So we're going to switch to the other version, which allows us to find the mass. Okay, and we'll know what the mass is based on the length of the object in the x dimension. Okay, so we have xcm is going to be equal to the integral of x dm over the integral of dm. So the first thing we're going to do is we're going to figure out what dm is. And we know that lambda is equal to dm dx, but lambda is also equal to alpha x. Therefore, dm is equal to alpha x dx. So this is what we're going to use for dm. So we get xcm is equal to the integral of x times alpha x dx over the integral of alpha x dx. Okay, so we can cancel out alpha. That's not going to be important to this problem. So in other words, if we think about it as trying to make a triangle out of a piece of plywood and then locate the center of mass, it doesn't matter what you use for the slope of the triangle. As long as it's a right triangle, it could be a thin wedge, it could be a thick wedge, that's always going to be proportionately the same. All right, so this becomes the integral of x squared dx over the integral of x dx. Okay, now what are the limits of integration? Let's take care of that. Well, this rod or this sheet of plywood, if that's how we want to look at it, it has a length of L, and of course each one of these chunks has a width dx, and so we're going to go from 0 to L. All right, so xcm is equal to the integral of x squared is 1/3 x cubed from 0 to L over 1/2 x squared from 0 to L. All right, so now we can simplify this a little bit, and we get 2/3 x. I'm sorry, 2/3 L. So we get 2/3 L, and all that's telling us is that in the x dimension, 2/3 of the way along the length, so we're looking at along this line here, that's not quite 2/3, but close enough, that the distance from here to here is 2/3 of the length of our triangle, of the base of our triangle. Okay, so that's all there is to it when trying to find the center of mass for a non-uniform distribution. You can imagine there are many other scenarios where it's not linear, and you can think of them simply as a piece of plywood which has been cut out, and we're just looking at it on edge. But to help you visualize the distribution, we can just think of it as though it's some shape, and that should help you out.